The next question is exercise 1.3.2. So this question says that show how to go from the basis so a certain set of basis vectors are given to us. So show how to go from the basis 1, 2, 3 in Romans to the orthonormal basis given as the following. So we need to show how we go from this top set of basis vectors 1, 2, 3 in Romans to this bottom set of orthonormal basis vectors 1, 2, 3 in numerics. Now this question is also based on the Gram-Schmidt orthonormalization that we saw in the previous video. So just to remind ourselves of what this Gram-Schmidt is, this Gram-Schmidt theorem, let us just write it down once again. So the Gram-Schmidt theorem says that given a linearly independent basis, we can form linear combinations of the basis vectors to obtain an orthonormal basis. And what is the procedure? How do we obtain it? What are the steps? We saw that in the last video. We will just recap that once again before proceeding to solve this question. So the procedure is: step 1, rescale the first vector by its own length. This rescaling by its own length is going to give us a vector of unit magnitude, that is a unit vector, because remember, for orthonormal basis we need orthogonal basis vectors of unit magnitude. So this is step 1. Step 2 is subtract from second vector its projection along the first, leaving behind only the part perpendicular or orthogonal to the first this subtraction of the second vector along this first one is this the first one obtained after normalizing it by its length. And then the third step is rescale the above leftover piece by its own length. So this rescaling again gives us a unit vector. So this is the second basis vector of the orthonormal basis that we are supposed to obtain. And then you continue this process. So what you do is continue this process. So what does that mean? Say consider the nth vector, then subtract from nth vector its projections along all the previous n-1 vectors So we subtract the projection of the nth vector from all the previous n-1 vectors that we have obtained from this process. These n-1 vectors are these unit vectors that we obtain after rescaling. And then finally, rescale by length to obtain a unit vector. So this rescaling is going to give us unit vector. So this is the general process, and now we will apply this process to solve this question. Let us come back to this question. So in this question, if you see, we are given these three vectors. Now, as we saw in the last video, that starting from different vectors as our choice for the first vector, we can come to different set of orthonormal basis vectors. So this Gram-Schmidt theorem or this Gram-Schmidt process does not give us a unique set of orthonormal basis vectors. So we need to be very careful in what is going to be our choice for the first vector. Now we can clearly see that this Roman numeral 1 vector and this numeric 1 vector are parallel to each other. Similarly, this Roman numeral 2 and numeric 2 vector is also parallel to each other, but the Roman numeral 3 and the numeric 3 is not parallel to each other. So let me write it down clearly for you. So we have this vector as 3, 0, 0. Then we have the second vector 0, 1, 2. This is the vector set that we are given with. And then we need to go from here to the following. Now from this, we need, as we saw that the Gram-Schmidt process gives us an orthonormal basis vector, but it does not give us a unique set of orthonormal basis vectors. So we need to be careful in the choice of our first vector. So if we select different vectors as a choice for the first vector, we will come to a final conclusion of different set of orthonormal basis vectors. So let us see what I was trying to mention earlier. We see that this vector is parallel to this. And why is that? We see that there is just a scaling factor. That is, if we take this vector 1 and then if we divide it by 3, we get this. So that means the Roman numeral 1 vector is parallel to the numeric 1 vector. Similarly, this is also true for the second vector. Why? Because again we see that there is only a scaling factor separating, differentiating these two vectors. Just scaling factor is there. But if we look at the third vector, then we clearly see that third Roman numeral vector is not parallel to the numeric 3, because we cannot write this vector as some scalar multiple times this vector. So our Roman numeral 3 is not some scalar multiple times the numeric 3. That means this Roman numeral 3 vector is not parallel to this numeric 3 vector. So that means our choice for the first vector that we are going to take should be either 1, the Roman numeral 1, or Roman numeral 2. Why? Because these vectors, just scaling them, rescaling them by some factors, that factor is the length of this vector. So just by rescaling Roman 1 or Roman 2, we are able to get numeric 1 and numeric 2. So our choice of the first vector should be either Roman numeral 1 vector or Roman numeral 2 vector. So let us select our first vector as the Roman numeral 1. So we have now, what does the process say? It says rescale the first vector by its own length. So what do we get by rescaling? So the length of this vector is clearly 3. So we get 1 by 3, which is nothing but 1, 0, 0. And this is how we obtain the first vector. Now the process says that subtract from second vector its projection along the first. So let us take the second vector. So for the second vector, take the second vector, subtract its projection along the first vector. What does that give us? That gives us basically second vector is 0, 1, 2. We will subtract from this the projection along the first, so let us solve this. So this right here is 0 if you take, so 1 into 0 plus 0 into 1 plus 0 into 2. So this gives us 0 minus 0. So this is nothing but 0, 1, 2. And then the third step says rescale this leftover piece by its own length. So we obtain the second vector just by rescaling it. So the length of this, the length of the second vector is nothing but square root of 0 squared plus 1 squared plus 2 squared. This is square root 5. So we obtain the second vector. Now similarly for the third vector, what does the process say? Process says continue this process, that is, consider the nth vector and subtract from it its projection along the previous vectors. So we have this third vector, we will subtract from it the projection along the first as well as the projection along the second. So the third vector is, take the third vector, subtract its projection along the second vector as well as subtract its projection along the first vector. So let us see. Our third vector is 0 to 5. Subtract its projection along the second vector. This is the projection along the second vector, and then projection along the first vector. Let us just solve this. Sorry, this is 2 over root 5. So this is 0 times 0 plus 1 by root 5 into 2 plus 2 by root 5 into 5. That gives us 2 by root 5 plus 10 by root 5, 15 over root 5. Then we have 100. Then this coefficient, if we see, multiply 1 with 0, 0 with 2, 0 with 5, what you obtain is 0. So sorry, wait, I think I have made a mistake over here. This is not 50, this is 1 into 2 plus 2 into 5, that is 12. Sorry for this mistake. So let us see, what do we get? So let us take this root 5 in the denominator outside, and then we have another root 5 in the denominator outside. So we get 12 over 5. Root 5 into root 5 gives us 5. And then we have 0, 1, 2. And then this is nothing but 0. So what do we get? Let us see. Get 0, 2 minus 12 by 5, and 5 minus 24 by 5. So let us simplify this. 0, 10 minus 12 by 5, and 25 minus 24 by 5. This gives us 0, minus 2 by 5, and minus 1 by 5. This is what we get. Now what does, so the its final step says, it says that rescale by its length. So we need to rescale by its length. So the third vector is this over the length. Now length of 3 of this 3 prime, it's nothing, sorry, this is not -1, this is +1. So the length is 2 by 5 whole squared plus 1 by 5 whole squared square root. This is, take 1 by 5 common outside, 2 squared plus 1 squared. This is root 5 over 5, which is 1 over root 5. So this is the length. So our third vector is dividing it by its length. So the length is 1 by root 5. So this divided by 1 by root 5, this gives us root 5 times this. Sorry, this is not root 5. This is just 5. So what do we get? We get so this is the final third vector. So we have solved this question. We have obtained 1, 2 and 3. So we see here we have 1, then we have 2, then we have 3. These 1, 2 and 3 are exactly the same as what we wanted to show in this question, starting from the Roman 1, 2 and 3. So we have solved this question using the Gram-Schmidt theorem, the Gram-Schmidt orthonormalization procedure, and we have obtained this set of orthonormal basis vectors starting from a set of basis vectors which were not orthonormal. So this solves this question.